Hi all, and welcome back. So we're going to be continuing from last time. Basically, as a quick recap, what we talked about is how a linearly independent set that spans the entire vector space gives us a basis. And that a set of bases is different than an ordered basis. And so we defined how these things are, but we never really defined, like, it gives us a nice way to look at the vector space, but it doesn't really specify why in particular they're very important. Like, how does this actually help? And it turns out the following theorem kind of helps answer that. And the following theorem is basically saying that a set of vectors forms a basis if and only if any vector can be expressed uniquely as a linear combination of those vectors. So in other words, there's only one way of doing this. And this is a very important word. So in this theorem, uniquely is the most important word in the entire thing. So remark, the most important word of this theorem is uniquely. And that's because there's a unique way of doing this. Now imagine, like, this is not a trivial fact, right? There could be that I have two different ways of representing the same vector. Like, we don't actually know this. But it turns out if we have a basis, then this is going to always be unique. Which is really, really nice. Now, if we want, we can actually see when this is not the case. So what we're going to do is we're going to look at when this is not the case. So we're going to take a set of vectors. We're going to have them span V, but we're going to remove this linearly independent condition. And we're going to say, okay, let's have something that's dependent. So what we're going to do is we're going to have a set of vectors. So here I have a set of vectors x1 and xm. They span V. And I'm going to have it equal to some vector x. Okay, so we have this linear combination. We're happy. Now, if they don't form a basis, that means they're linearly dependent, right? That means there exists some choice of the scalars such that this linear combination, and remember what this means. This is saying, or I guess there exists some choice of non-zero. This should have the word non-zero here. Scalars such that this linear combination is equal to 0. That's basically what we defined linear dependence as. Well, what this means is, since this is just equal to 0, right, I can just take this and add it to that, right? So think of it this way, x plus 0, well, this is just x, right? This doesn't really change on the left-hand side. But here, this x is lambda 1, x1, all the way up to lambda m, xm. The 0 is precisely what we had before. Oops, this is 1. That looks like an I, right? So this is x plus m. X plus 0, sorry. And if we add these together, what we see, these are just other scalars, right? So what I can kind of do, yeah. So here's another way to write x. So it's no longer unique. And that becomes problematic. So that's why we really require this linear independence there. Now, one thing you probably also clocked was that I never said the basis. Well, I hope I never said the basis. And that's because we're always going to talk about a basis because there's many different choices of bases, right? And so there might be multiple different ways. But one thing that always holds is that the size is always the same. So they always have, every basis of a given vector space has the same size. And this gives us what's called the dimension. So the dimension is nothing more than just the size of the basis. That's it. Super simple. So if that's the case, we should come up with some easy way to figure out what a basis is as a vector space. And luckily, there's a nice canonical, normal, fancy, not fancy, super easy way to get a basis of R to the n. And this is called the canonical basis. So here, let's recall kind of the standard vectors that we see in R to the n, right? So these are just the column vectors. And what we're going to do is we're going to choose some set of vectors that kind of give us every single possible vector. So E1 we'll set as 1, 0, 0, 0 all the way down. E2 is going to be 0, 1, 0 with zeros all the way down. E3, can you guess what this is going to be? 0, 0, 1, 0 with zeros all the way down, all the way up to n. And it turns out this is a basis. This is probably not too hard to check. So it's nice and easy. And the nice thing is we can take any vector, any vector A, we can express it as a linear combination in the following way. So A is just going to be A1. So we take the first letter of A. So here I should maybe look at A. I'll write it down here. A is equal to A1, AN transpose. So I take A1, right? So this is the first thing in our thing. Actually, let me write it this way, so we can kind of see what it looks like. So here, to take this first component, I can just take A1 and I can multiply by the first one, right? So I can this just adds an A1 to the first one. Then I can add a A2 in the second entry, etc. all the way up to AN. And this you can kind of see already gives us exactly the basis that we have been talking about. E1 plus A2 E2 plus AN EN. And so this we call the canonical basis. And it's used very heavily in a lot of the stuff we do. So we'll actually define it. It's obviously, just like we talked about, not the only choice of the basis, right? So we already saw in R2 an example of something that was not a canonical basis that spanned all of R2. But it does give us a very nice basis. And so we do use it quite frequently. One quick remark before we kind of end this section is that so far we've been talking about finite things. So everything has been a finite set, but there are infinite dimensional vector spaces. So one example is if I take R, like polynomials in one variable. And what this is basically saying, so we denote it by Rx in brackets. And these are polynomials written in this way. X, so the variable here is x squared, cubed, forever. Like it doesn't stop. And all of the AI are going to live in R. Right? So this is the basis. Sorry, this is a, I guess it didn't show up, sorry. This is a vector space. Now the basis for this vector space is going to be precisely the elements 1, x squared, x cubed, xn, basically forever. Like it doesn't matter. So since there's an infinite number of basis vectors, this basically means that we have an infinite dimensional vector space. Quick exercise at home, if you ever want to try, show that this is infinite dimensional vector space. Don't be put off by the word infinite. It's actually really fun to do. So just try it out, have fun. But yeah, so I'll see you next time for change of basis and transition matrices.